So in this video lesson, we're going to be looking at why is it that chemical bonds form in the first place. One theme that we've used throughout the whole course is we have talked about atoms want to be stable. So the reason that chemical bonds would form is because nature likes to be at the lowest energy level. That is what is more stable than any other situation. So if a chemical bond forms, what always occurs is energy will be released. And by releasing energy, the atoms are put at a lower energy state, and therefore it makes the entire molecule more stable once the elements have obtained their octet rule. If a chemical bond were to break, energy would have to be added. Just like if you were going to break a stick, or if you were going to break a piece of wood or break a piece of chalk, you would have to input energy. Similarly, when a bond breaks, energy has to be input. Most atoms have a lower potential energy when they are bonded to other atoms. Now, I do say most atoms because, of course, your noble gases are already stable, so they don't typically participate in chemical bonding because they have their stable octet, or in helium's case, he has his stable duet. But most atoms will have a lower potential energy when they are bonded. So we're going to take a second to look at this bond energy diagram. Take a second to sketch this out. And we're going to be looking in particular at 3 points on the diagram. We're going to be looking at point 1, which represents the highest energy point that we see here. Then we're going to look at point 2, which is representing the lowest energy point here, which is what I would call the trough. And then point 3 would be the region where the energy starts to increase slightly after the atoms have bonded, but then it sort of plateaus off and stabilizes. And it does stay below this red line that I've extrapolated across my graph here. And as long as the energy stays below that red line, which I'm just designating here as a reference point, 0 potential energy, then the atoms will remain bonded. The only way you could break the bond is to add enough energy to bring it above this line, and that's what I was mentioning earlier, that bonds, if they break, energy has to be added. So on the next slide, we're going to be talking about why it's happening at point 1, 2, and point 3. So the explanation of the energy diagrams. At the point 1, that represents a point in time when the atoms are separate and the energy is at its highest. Point 2, that represents the energy where the stable molecule forms, and that's where we see the energy at its lowest point, and that would represent a stable molecule. As we approach point 3, and then as it starts to level off, what's happening is the repulsive forces do get a little stronger than the attractive forces. And when we say repulsive forces, we're talking about the forces between the two nuclei here, where you have your protons in the nucleus, and then of course you have your electrons in your electron cloud. So the repulsive forces would be talking about if the nuclei get too close together, there will be a proton-proton repulsive force because like charges repel. And if the electrons get too close, there'd be an electron-electron repulsive force. So as the atom is, or the bond is forming, there might be a time where the nuclei get so close together there may be some repulsive forces, but eventually the stable molecule forms because what happens is the protons in the nucleus of one atom will be attracted to the electrons in the electron cloud of the other atom, and therefore the atom will remain bonded as long as the energy stays below that 0 reference point that I mentioned. A couple of terms we want to be familiar with is bond energy and bond length. The bond energy is defined as the energy that is needed to break a chemical bond, and depending on the type of bond, whether it's ionic, covalent, or polar covalent, nonpolar covalent, or metallic, that would determine how much energy would be needed, and also if it's a single bond versus a double bond versus a triple bond, that would make the bond energy fluctuate. Another term is bond length. Bond length is the average distance between two bonded atoms, and we call it an average distance because you want to think of the bond sort of as like a spring. if you have two atoms bonded, and so the spring would be like moving in and out. So the bond length does kind of fluctuate depending on those forces I mentioned up here, the attractive and repulsive forces. But the bond length is defined as the average distance between two bonded atoms. Now, in our next video lesson, we're going to talk about Lewis structures. So we need to look at some how we represent shared electrons. So in our Lewis structures, we're going to see single bonds, we're going to see double bonds, and we're going to see triple bonds. So a single bond is represented by one dashed line, and that is two electrons being shared. So when we draw our electron pairs when they're not shared, they look like this. Two dots is unshared electrons, or called lone pairs. But when they're shared between two atoms, we do a single bond that represents two electrons that are being shared between atoms. So like X bonded to X. Then we might have a double bond. Double bonds are four electrons being shared, and it looks kind of like an equal sign. So if you were to have X bonding to X, and then they will be sharing four total electrons, that would be represented by two parallel lines. And then the highest bond multiplicity you could have is a triple bond, and that's six pairs of electrons, or six electrons being shared, so three pairs of electrons being shared. The longest of the three, single, double, triple, is the single bond. Single bonds are the longest, and your triple bonds are the shortest. Now, the triple bonds are also the strongest bonds that we have. Shorter bonds are always stronger than longer bonds. So remember the saying, shorter is stronger, longer is weaker. So the longest bonds are the weakest. That's your single bonds are weaker, and the shortest bonds, the triple bonds, are the strongest. Our next video will be on Lewis dot structures.